Now we're going to apply all of those, well, really basically everything we've learned up until now, everything about limits, the increasing, decreasing concavity, maximum, minimum, uh, you name it, everything we've done so far, and even some algebra and some trig to a trigonometry function. So before we get started, let's look really briefly right here at this cosine function. That's what I was trying to draw. Okay, I'm sort of sometimes drawing challenged. All right, so this is supposed to be the cosine function. Remember, it's if you look at it from 0 to 2 pi, then it starts at 1, drops down to 0 right here at pi over 2, goes down to -1, up to 0 at 3 pi over 2, and then comes back up to 1. Of course, it repeats, from -infinity to infinity. It has a period of 2 pi, but we are just going to talk about a version of this, okay, from 0 to 2 pi. So just keep up with where cosine is 0, right? Okay. So what we are going to explore is we are going to explore secant squared x. Now, secant is what I call a version of cosine because it's the reciprocal, right? Flip it upside down. So this is actually 1 over cosine squared x. And remember that that square is actually 1 over cosine x squared, because you may need that. Okay. You don't have to deal with the function the way it's actually composed, especially like with trig. If you're not comfortable with secant, then when you're trying to figure out where secant is equal to something, then try to think of where cosine is equal to 1 over that. All right. So let's talk about all of our little steps. And we'll flip kind of back and forth between talking about secant and talking about cosine. And we're only going to talk about the interval. Now, mind you, secant goes on forever as well, right? But what we're going to do, as soon as my computer unfreezes, which it seems to do at the same time every time we get started on a video, we're going to talk about it from 0 to 2 pi. So we're going to limit our discussion. Otherwise, we would have all these plus n pi or n2 pi or k pi or k2 pi where we used to do these repetitive things. So let's talk about the domain. Now, the domain for cosine is -infinity to infinity, right? But remember where cosine is equal to 0, right? When you take 1 over 0, that's undefined. So secant is undefined. When cosine is equal to 0. And for the interval that we're talking about, it's equal to 0 when x is pi over 2 and 3 pi over 2, right? Okay, so when x is pi over 2, 3 pi over 2, cosine is equal to 0. 1 over 0 is undefined. So for secant, x can't be pi over 2 or 3 pi over 2. So its domain, now, okay, its domain is actually -infinity to infinity, and every pi over 2 interval, it's has a problem, has an asymptote. But we're just talking about 0 to 2 pi, so we're going to start at 0. Going to go up to pi over 2. On the other side of pi over 2. And then from 3 pi over 2 to 2 pi. Now, sometimes, not very often, but sometimes people think, well, why can't I just say the domain is 0 to 2 pi? Well, we're going to draw it from 0 to 2 pi, but right in here, everywhere we had this little gap, there was going to be a vertical asymptote. So it doesn't actually have a point there. So in case you were wondering about that, that's the answer. Now, we're looking at x-intercepts for the next step. And for where the x-intercepts would be located, that would be where y is equal to 0. And so this would be saying, well, where is 1 over cosine squared x equal to 0? Well, okay, notice that there's 1 in the numerator, and you get 0 from where the numerator is equal to 0, and 1 can't be equal to 0. And if cosine x is equal to 0, it's undefined, so there are no x-intercepts. And then for the y-intercepts, and you may be already going, I know what this looks like because I can imagine what secant is when you square everything, but the importance here in this concept of going through this problem is working those trig muscles, right, and trying to see how all this fits together. And there's a lot of nuances in here. And so let's just trudge our way through here, even though you probably have a good idea of what the drawing looks like. You may not. It's okay. We'll get there. All right. So to find anybody's y-intercept, you make x be 0. And so in effect, what you're doing is saying, in case you're unfamiliar with secant, you've got this. And cosine of 0, remember, was 1. So this is 1 over 1 squared, literally. So y is 1. And so you have the 0, 1 as your y-intercept. Now for symmetry, you replace x with negative x and see if you can get back to the original or the opposite of the original. If it's an exact match to the original, it's even. So if it's an exact match, it's even, which is symmetric to the y-axis, or with respect to, I should say with respect to. With respect to the y-axis. And if it's the opposite throughout and everything has to be the opposite of what it was, it's considered odd. I like seeing little patterns, exact and even, opposite and odd, which is symmetric with respect. I should try to make that look like 2 words. With respect, goodness, to the origin. And this one kind of matches all the way down. All right. So this, and in case you're like, I'm not sure what secant's doing, this would be asking you what 1 over cosine negative x squared is doing. And you remember from trig, there was an identity that said if you have the cosine of a negative angle, it's the same thing as the cosine of the positive version of that angle. So this is 1 over cosine squared x, which is secant squared x. So it's an exact match to the original, so it's even, so it's symmetric with respect to the y-axis. Now we're staying to the left of the y-axis, but it's important to know. And for the periodicity, all right, so you know from trig that the normal period for secant is 2 pi, right? It takes 2 pi to get through the positive values and the negative values for secant. But since we're squaring it, all we have to do is get through all the positive values because we're going to repeat that all the time. So this periodicity, it repeats itself every pi. Then we're going to look at the vertical asymptotes. Now, we had them for our little interval, pi over 2 and 3 pi over 2. So let's talk about the limit as x goes to pi over 2 from the left for secant squared. This is actually equivalent to the limit as x goes to pi over 2 from the left of 1 over cosine squared x. Okay, so this would be 1. And coming in to pi over 2 from the left, way back up here. Coming into pi over 2 from the left, you've got a little bitty tinier and tinier and tinier and tinier and tinier positive number as you're getting closer and closer and closer and closer to 0. So this is going to be a tiny or a wee little tiny positive. I actually say wee little tiny to students because it makes them smile. Okay. And then you're going to square it, which makes it even more tiny or tinier. So anytime you divide by a little bitty tiny number, you're going to get a huge number. So this turns out to be positive infinity. So the limit as x goes to pi over 2 from the left of secant squared is this. Okay. Then we're going to do the limit as x approaches pi over 2 from the right of secant squared, which is the same thing as the limit as x approaches pi over 2 from the right of 1 over cosine squared x. And if you'll remember, as you're coming into pi over 2, from the right, you've got a little tiny negative number that's going to get closer and closer and closer and closer and closer and closer and closer to 0. So you have 1 over a little tiny negative number squared, which makes it turn out to be 1 over an even tinier positive. So you get positive infinity again. Now, one of the benefits of having something that has a period and having a periodicity of pi for this particular problem says that when I come up again for the limit as x goes to 3 pi over 2 from the left, since its period is pi, and this is pi over from here, okay, then you can use periodicity to justify the fact that this is going to be positive infinity as well. And likewise, the limit as x goes to 3 pi over 2 from the right by periodicity is going to be related to this one. And so it's going to be positive infinity as well. All right, now horizontal. Now, what we would want to know about this is what is it doing as x goes to plus or minus infinity. And as you know from the trig functions, they just cycle through whatever they're doing, all the way. They don't get out to infinity and settle down in a particular direction or settle down at a particular value, so there are none. Now let's do the first derivative. So it's been a while since we saw back up there. And that was our original function, but to take the derivative, it's probably a little easier for you to think of it mentally or by writing it down, either way, as secant x squared. So the derivative, bring the 2 down, leave the inside alone, take 1 off the power, loop back in and take the derivative of the inside. And it looks like 2 secant squared x tangent x. And this is the derivative. Now, for what we're going to be doing next, you don't actually have to leave it in that shape because we're going to be looking for critical values. Some people call it critical points. It might help to think of this as 2. And remember, tangent is sine over cosine, and secant is 1 over cosine squared. So you get 2 sine x over cosine cubed x. And that may help you to think of how we're going to find our critical values, critical numbers, however you want to think about it. All right. So where is the numerator equal to 0? Well, sine's equal to 0 at 0 and pi, and then it repeats every pi, right? So it's actually 0 plus n pi or k pi, however you want to say it, it repeats. So, but for our little slice, it would be 0 to pi. It actually happens again at 2 pi, but remember for our interval, we were saying it's 0 to 2 pi, but this is an open-ended on this side, this is closed on this side, and so we don't actually get to the 2 pi, so we're going to leave that out. So, and then it's undefined when cosine x is equal to 0, and you probably got this memorized now. It happens at pi over 2 and 3 pi over 2. So what we have is the sine chart, and it's going to start at 0, and it gets out here and stops right before 2 pi, but I'm going to put it there so you can remember. And here's 3 pi. Here's pi over 2. And over here is 3 pi over 2. There you go. All right. We've got that down. Now, so here we go. Now we need little test points, right? So in between 0 and pi over 2, pi over 4 might be nice. Okay. Maybe I'm going to stick with pi over 4 multiples because I'm comfortable with that value for both sine and cosine. And it just makes my life a little easier when they all match. They say variety is the spice of life, but y'all, when it comes to math, it's kind of like let's just try to make things a little simpler as much as we can. All right. So we're going to have our test value. We're going to look at our sines, and then we're going to find our resultant sine. Okay. Now, what I'm going to use to figure this out is this 2 sine x cosine cubed x. And so this one's always positive, right? So when x is equal to pi over 4, this is actually quadrant 1. So everybody's positive, right? And so you have your plus 2 times your sine of x right here. And sine of pi over 4 is the square root of 2 over 2, which is positive, over cosine cubed, which is square root of 2 over 2, positive, cubed again. All right, so this is positive, right? If you have x is equal to 3 pi over 4, you're in quadrant 2. Okay, 2 is always positive. Sine of 3 pi over 4 in quadrant 2 sine is positive. In quadrant 2 cosine is negative. So you have a negative cubed. So this turns out to be negative. X is 5 pi over 4. This is quadrant 3. So 2 is always positive. Sine in quadrant 3 is negative no matter what's going on. In quadrant 3, cosine's negative no matter what angle you're at. They're both negative. So you have a positive. X is 7 pi over 4. You're in quadrant 4. 2 is always positive. Sine in quadrant 4 is negative. Cosine in quadrant 4 is positive. So this ends up being negative, so it bounces. Plus, minus, plus, minus. So it's going to go positive, negative, positive, negative, right? That's kind of your little image thing you got going on there. All right, so this part was the first derivative. This part in here, seems like we're always leaving it out, gets buried in there, is your critical values, critical points, critical numbers, and the sign chart. I think I've told you that this list is something that my classes develop. And I had a tendency to lump these together. That's, I guess, why I keep forgetting I. And they pulled them apart so that they wouldn't forget to do that. And I keep forgetting to do that. Okay. I do it. I just forget to label it. All right. So here we go. So this is the critical points or values or numbers, whatever you call them, in the sign chart. So then what we're going to do is talk about where it's increasing. I used to lump this other stuff together too, but whatever helps them stay afloat. All right. So looking at where it's increasing, it's between 0 and pi over 2 and pi and 3 pi over 2. 0 and pi over 2 and pi and 3 pi over 2. Sometimes the littlest things can help you to stay calm and vigilant. Okay, so where is it decreasing? It is decreasing between pi over 2 and pi and 3 pi over 2 and 2 pi. And 3 pi over 2 to 2 pi. And again, when you combine these things, looking them over, looking at these two, you should have that whole interval taken care of, represented. So here's, the first one actually. Here's the second one, third one, fourth one. As you're working across the interval, it just helps to double check that so that you don't accidentally leave an interval out if you've got a very complicated problem. So we're going to talk about the minimum, if there is one. So if you look at the sign chart, it appears to have kind of a little valley right here. So x equals pi. So y is secant squared of pi. So it is negative 1 squared, which is 1. So this is pi and 1. Now, but even though it's really not necessarily looking like a valley, it's sort of like part of a valley right over here. 0 is the end of that interval, but it's included in the interval. So let's look at x is equal to 0 for a second. So when x is equal to 0, y is secant squared of 0. Remember, it turns out to be 1 squared. So this is 0 and 1. And you could think about and go, well, hey, if I'm going to do that down here on this left side, maybe I should do that over here on the right. But remember, 2 pi is not actually included in the interval. It's open on that end. So we're going to leave that one out because we never actually get there to 2 pi. All right. And then let's look at the maximum. Oh, now also these, and I'm kind of open for discussion. If y'all were actually in the class, we would talk about this. So they are definitely local because the local says that you're the lowest point in that area. So they're definitely local. I don't know that I'd call them absolute because it's like a tie for the absolute. And to me, if it's an absolute, there is only one. It is the absolute lowest point in the whole curve. And since there's a tie, I think of these as local, right? And then for the maximum, now, if you look back up here at the sign chart, it looks like there's this mountaintop thing going on right here at the top of a hill. And so it sort of implies that there might be a maximum there. But if you remember, keep going back to there is an asymptote here. There's a vertical asymptote there and here. And so there is no value there. Okay, there's a break. And this is actually just reinforcing what we knew about the limits that we did earlier. Okay, so there's not a connecting piece to tie these two together, so there is no maximum. Okay, we're getting there. Okay, second derivative. Let's see if I can remember to do the next part separately, like I did not do on the first derivative. You gotta have a goal. All right, so the first derivative looked like this. Okay, so the second derivative would be, here's your 2. It's the first times the derivative of the second, and the derivative of tangent is another secant squared, plus the second times the derivative of the first. So remember, this is secant x squared. So you'd bring down the 2, leave the inside alone, take 1 off the power, loop back in, and take the derivative of the inside. So it looks like this. So you have 2 secant to the 4th plus 2. Let's see, we could clean it up and have a secant squared x tangent squared x. That's a little bit better. Okay. There's a secant squared in common, so let's see what we can get after we do that. So we'd have secant squared x plus 2 tangent squared x after we factor out the secant squared. And these that are in the parentheses, this secant squared is actually 1 over cosine squared, and the tangent squared is actually sine squared over cosine squared. Okay, so we could make a single fraction out of those because you could try to set up where these would give you a critical value or critical number and say where they equal to 0, but it works best if you have a either factors or division, because trying to do it where you're trying to see where they're equal may not be very apparent. So you'd have 1 plus 2 sine squared x over cosine squared x. And I think that's where I'm going to say good place to stop. I can live with this. Well, I could live with that if I didn't just draw right through it. So this is 1 plus 2 sine squared x. We'll start up here. There. All right. So here we go. I remembered. Okay, so then we would have our critical values, critical numbers, critical points, whatever you want to call them, and our little sign chart. I like the sign chart. Okay. So the question then becomes, oops, I lost my square right here. So then, oh, we could clean it up just a little bit more. Hey, let's talk about that. I just noticed. We could take this and see how it's a secant squared. We could actually drop this down in there and have 2 times 1 plus 2 sine squared x over cosine to the 4th x. That's actually even a little nicer. Let's use that one. Okay, so this would be f double prime x. Alrighty, good one. All right, so if we have this version, let's do this version. Okay, well 2 is always a 2. 1 plus 2 sine squared x would give, if we could get 0 in the numerator, that would give us 0. But if you think about it, this is sine squared x is equal to negative 1/2. And you can't square any value of sine x and get a negative, right? You'd have to start off with some sort of imaginary angle or whatever. So not going to get anything from here. Okay. And then from the denominator, it's the same old, same old. Where is cosine x equal to 0? Because that's where it's going to be undefined. And for us, that's going to be our pi over 2 and 3 pi over 2. And so our sign chart starts at 0, goes to 2 pi. Now down here it's closed. Over here at 2 pi it's open. Here's pi. So this is pi over 2 and 3 pi over 2. All right. Now let's talk about this for just a second. All right. So what we have is 1 plus 2 sine squared x over cosine to the 4th x. Correct? Okay. Now let's talk about this. All right. So the 2 is always positive, right? You take sine of anything and square it, it's going to be positive. Multiply it by 2 and add 1 to it, it's going to be positive. And you take cosine of anything, and whether it's positive or negative, you raise it to the 4th power, it's going to be positive. So no matter where you are, okay, they're all positive. So all of these areas, okay, are going to be positive. So it's always concave up, because we only need that one. Okay, so where is it concave up? Anywhere there's a part of your graph. So from 0 to pi over 2, from pi over 2 to 3 pi over 2, from 3 pi over 2 to 2 pi. Where is it concave down? Nowhere. So you could say nowhere. You could say none, NA, whatever you want to say. And where are their inflection points? Well, since it is always concave up, it doesn't switch over, so there are none. Okay, now all we have to do is remember to graph it. Okay, so we had a y-intercept at 0 and 1. We know we had a vertical asymptote at x is equal to pi over 2. This is pi. This is 2 pi. We had another vertical asymptote at x equals 3 pi over 2. All right. Now, and we know that we had another kind of a local minimum, if you get back up here, at pi over 1, which is supported really by this concept of the period that every pi, it's going to repeat itself. And based on our limits, it looks like this, which basically looks like you took the secant curve and made everybody flip positive. Now this one down here is technically open because we're not getting to 2 pi, but I think you kind of get it. All right, and that's the trig one. All right, we're almost done with this graphing section. I'm going to throw the optimization in here next, and then the video after that will have a really quick review and then a practice test where it puts it all together. Not nearly this detailed. Okay, it'll be just like little bits and pieces, and then we'll move on. And the next grouping of videos will be over antiderivatives and integration. And a lot of people really like that. I do too. All right, see you at the next video, and please remember to like and subscribe.